Whereas for neural networks, it's a little more hand tuning and setup involved in the beginning. But we can also, get a neural network that runs in a simulation. And the big important thing to note for these two different models is that property of random forest, where they don't really extrapolate outside of the domain of the training data that I've seen. Whereas the neural network will, bravely extrapolate if you give it a new point that it hasn't seen before. So this, so this is, makes it for really good performance in the offline setting for neural networks. And we typically see that they do better than random forest, which I'll show in just a little bit. But it also makes them a lot more finicky when we go and plug them into a model and couple it to the fluid dynamics, because it's pretty easy for a neural network to give some pretty extreme predictions. Okay. So here's an example of an offline prediction of a random forest model versus a neural net. And then on the left here, we have sort of the target data. So you can see that the neural net is generally doing, they both get the large scale patterns, but the random forest isn't really getting any of these areas of cooling. It's basically doing mostly heating. And the neural net is doing a better job matching the amplitude to the random forest. Doesn't get the full amplitude of the training set targets. And then here's an example of a neural network that actually blows up when you go and plug it into a simulation. So basically this black line here is what we use as our baseline for comparison. So it's just the sort of the regular climate model that doesn't have any machine learning, and it's using its regular parameterization to describe convection. So you can see that runs in just a little bit, but it doesn't crash. And then this blue line here is a neural network that we trained that didn't crash. And then what I tried was, let's try and add some additional outputs. So let's try predict wind as well, and do some momentum corrections in this model. And so I don't have it shown here, but the random forest just handles this really easily. You just have it, predict some momentum, and it still runs. Whereas this green line here is a neural network that's trying to do the same thing, and it just goes crazy. We have made big improvements in keeping neural networks stable. So I don't want you to take away that this is what they're all doing. I'm just trying to show the dangers of using a neural network in these simulations. And one interesting thing that you guys might appreciate is a really easy way to increase the stability of a neural network is to just use a mean absolute error loss instead of a mean squared error loss. Since it's going to make the machine learning less sensitive to outliers in the training data, and therefore less likely to predict an extreme value when you use it in an online setting. Okay, almost done here, so I won't spend too long on this slide, but the point is just that these models do have increased weather forecast skill over our baseline, which is good. So basically what this is showing is that you get about an additional day in forecast lead time improvement if you run a model with the machine learning parameterization. Okay, thanks for listening. I'll just leave you with this fun little animation. So this is a high resolution model, and then this is a machine learning model that was trained to try and replicate it. This is showing, I think, rainfall over a day or two.
Oh, awesome. This is really cool. I didn't know you can just make the world map to flat and just watch all the rain. How do they flow? How do the air and water moisture flow? This is very interesting. Yeah. So the application is more about global model, and the units maybe several kilometers, several hundred kilometers. It's not about within a city, you can see when it's going to rain.
Right. Yeah. So even in this high resolution video, this is actually downsampled from the original high resolution at 3 kilometers, because that would have been way too much to make a movie of.
Yeah. Got it. That makes sense. Yeah. Awesome. Thank you
And
for
I'll actually talk about applications a lot. So it's a nice tee up.
yeah.
I
Yeah.
actually have a question, Anna, that I could ask you that's kind of relevant. So kind of, and I even teed us this idea. So my talk will absolutely be about the application of models like these. Our team does less ML, right? And does more just ingesting kind of a lot of the downscaled models that other scientists have done. The temperature and precipitation, any of the meteorological variables that we use in ours, it's a public data source, but the resolution is 3.1 and change kilometers squared. So according to, like you, that would be like very high resolution. I don't think I saw in reading the methodologies of that work that it was driven by machine learning that they do that downscaling. It looked like kind of a little bit more, I don't know, what do you think it was, are there other techniques that are kind of not machine learning, but maybe more, I don't know, kind of your traditional kind of statistics relationships? Because I know that it's not necessarily the modeling that they've done, because I know that there's the two sources of downscaling where you can, model it out, right? Simulate it, and you run the simulation in the future, or you take kind of the global projections and then you use the statistical relationships between like global averages and local locations to then, I think that's the technique that our sources kind of use. Is there, when you think about, you said that this is publicly, you guys, this will be public stuff that you guys do. And when you present these, have you compared kind of what you'll be capable of versus those public sources? Or
yeah, no, that's a good question. I'm unfortunately not very familiar with those sources, but you said, so it's like you're saying 3 kilometer scale
3 kilometers
projections
squared.
out decades?
Yeah.
Huh.
To 2060. Let's talk offline.
Yeah, that'd be really interesting.
Because because we're building product off of it, right? And it's like a public source is like validated by, climate scientists. So you like to think like, oh, okay. Like, but let's talk offline. I want to talk about, different.
Yeah.
I'm really interested. Yeah, I don't think it would be, like a directly simulated thing, but yeah, I'm sure they have other,
Yeah. And then I haven't done a lot of thought yet into like, and maybe you would have already done this thinking. So let's definitely talk about it. I'll buy you a virtual coffee, but like, what are the advantages, right? I mean, because in one situation, maybe in this statistical model, I can get more local, but I'm not really getting local with any kind of accuracy maybe, or I don't know how they've, how do you validate into the future?
Awesome. Like it's always exciting to see people got connected in our like events, and maybe we can start a panel about it next time.
Yeah. And Tia just asked, I'm talking about these regional downscaling where global models feed more localized models. That's what I am talking about. That's like our sources that I'll talk about next for climate check. They've done that work to do the downscaling. We have advisors that help us do that with drought and wildfire because it's different, right? It's different kind of sources, and flooding is different sources, but the temperature and the precipitation are this like 3 kilometers, and it's been, okay. So it's a totally different, when they do those local models that nest within the global ones, it's different. They're not using probably machine learning techniques. Tia, is that, I'm like tracking Tia in the chat. Yeah, I wonder how the methodology compares. Tia wants to know too. Let's invite her to coffee as well, Anna. You, Anna, Tia, and I, we'll have coffee and we'll talk about this.
Sounds good. Yeah, sounds like a good idea.
Yeah, okay. And Alexis can come too. I'll send it around. We'll do another group meet.
Yeah.
Okay.
Yeah, let's get to Alexia Hoffman's question. Hey everyone, I'm Alexis Hoffman. Hello, Alexis. She says, I'm a climate scientist turned data scientist. I'm located in Boulder. Awesome. Well, I couldn't miss those talks. Excited to be joining you. Yeah, we are very happy to have you here as well. Looks like you guys are training with the GFDL model. How do you think these models would perform using another model like CESM or MIROC as inputs? particularly one with different regional biases? Do you want to address this question, Anna?
Yeah, sure. Yeah. Hi, Alexis. I'm probably not the best person on my team to be answering this because I'm like the one person who didn't come from a background in atmospheric science. But I can say we have done this. Like we have used different data sets. So for the results here I was using a GFDL shield model, but we have also sort of used like a reanalysis data set as the target as well. And yeah, you're right. It definitely does change the resulting model. Like if you have a different bias in the training data set, you definitely see that in the online run.
Hmm.
And if you like have one that's too biased, then it tends to just lead to more instability and crashes and drift.
And that initial graph that you showed, where it showed the kind of incredible disparity in different people's forecasts for precipitation, is that different regional biases? Like, and they're all kind of capturing the global picture still, or what was that like? I know or is it, just like not elements of that in it? It really just is like you parameterize these things differently and they will come out with, outrageously different numbers, even if you're using kind of the same inputs.
Sorry, so you're asking like if you start with the same inputs and just have a different parameterization, like is that
Well,
what's
no, I mean,
leading
I
to
know
the
if you have a
start?
different parameterization, it'll make a big deal difference. But like when you showed that graph, right, and you showed all the different forecasts into the future, my first thought in my mind was, are they, I guess, like this idea of like the regional, like if I'm trying to target, or if I have better data in some regions versus another, or I'm, in terms of what you're capturing, like where, I don't know, but maybe it doesn't even work that way. Yeah, like a regional bias that kind of goes through. But
Like, are there some regions that have more agreement in models than
yeah,
others?
maybe.
Yeah, I think there's definitely like some there's global maps that can show you like the spread in the ensemble for different predictions. Yeah, I'm not too familiar with it though, but I bet like the climate science the people with like climate science backgrounds are all like, yeah, those regions
we
got,
should
like,
definitely
way more
start
uncertainty.
a climate scientist group within
Yeah.
our online machine learning data science group, and we also are planning to have a second round of talk about climate change, so hopefully more people will be connected at that time. Yeah.
Nice.
Okay, we got some more questions coming. So actually, I posted a question like I'm not quite familiar with climate scientists, but climate change models. But I'm just curious. I see you are dealing with a lot of data. I'm curious what tools you use to do the modeling. Like, do you use Spark? Do you use Python? Or do you use R? Or is it any specific languages or tools that's particular fit for climate change models?